Hello everyone. We are excited to present a realistic approach to combining renewable energy resources to generate power and directives that involves anywhere from agriculture to pharmaceutical industry. So we evaluated our value propositions through economic metrics such as NPV and levelized cost of energy. I am Shah Kabir, and my research partners are Jose Benavides and Pushpesh Sharma. They will join us in this presentation. So what motivated us? We found that the solar day cycle can be juxtaposed with the night cycle of thermal energy extraction. So what we wanted to do is explore the technical and economic merits of the two basic energy resources that I just referred to. So as I indicated, that will be for direct use of different industries and indirect use for power generation. We'll get into details momentarily. So where are we? Well, we are uh, dependent on the traditional oil and gas resource, and the low carbon solutions are coming to our to serve us along the way, but it will take time, as you can see. So what are the prospects in the US? As you can see, the western states are desirable for generation of power given the high geothermal gradient. So in contrast, the yellow states are of a lower capability in terms of ability to generate uh, hot water. So that's why they are more suitable for direct use, such as we mentioned earlier, from agriculture to pharmaceutical industries, depending on how deep the well is and so forth. So what are the mechanisms that are in play, the green energy resources? So the first option we are considering is the reverse circulation. So we are circulating down the annulus and up the tubing. So the idea is to extract thermal energy uh, from the formation, and keep in mind that this is a closed loop system. And in terms of what we do is that we use a numerical model in the wellbore to estimate the fluid uh, and heat flows for a given circulation rate in the wellbore, and an analytical model for estimate the heat flow in the reservoir. So we have the combination of two approaches. And in terms of solar power, we did consider this smart flower, which is highly efficient, but it's quite expensive compared to the normal solar panels that we can see in rooftops. Okay, so it is a we just looked at the fluid circulation loop, and now we put it through the heat exchanger and then generate steam into the turbine to power generator. We also have an option that we created because for the natural gas, and the reason for that is yeah, we want to stay green, but the point is this is a backup strategy. So we are considering 25% of our energy generation on this natural gas. And so that's how we want to approach the problem. And then, of course, we have the solar panels, regardless of the type. And we go through the energy converter into the transformer and finally onto the grid. So that's all I had. And now I hand it over to my research partner, Jose Benavides. Thank you.
The big disadvantage of producing energy by continuously circulating fluid in a closed loop is the significant decrement of the geothermal gradient in a small amount of time around the well. To overcome this issue, we propose an intermittent circulation with periods of circulation and non-circulation. This way, the geothermal gradient is not significantly affected, thus the energy extracted from the well will be much higher. To compensate the lack of energy during these shut-in periods, another source of energy will be implemented. For instance, a twin well or a solar panel. This graphic shows the intermittent approach using twin wells. The wells are located at a distance that interference between each other is null. By producing energy from two wells at different periods, we are providing a constant energy flow and conserving the geothermal gradient, which is ideal for indirect use. It is evident the huge difference between the intermittent and the continuous flow with respect to the outlet temperature. The same trend is followed by the power generation. The main message here is that the twin well approach is most efficient for energy extraction. In the previous slides, we have shown the potential way to improve the energy extraction by circulating in periods of circulation and non-circulation. But what about the fluid? Another way to improve the energy extraction is by selecting an adequate fluid. After evaluating different fluids, pentane proved to be the best option. It overcomes water in terms of energy extraction, being ideal for indirect use in regions with high geothermal energy. Now that we have seen the technical side of this project, let's dive into the power demand and supply. The average annual power consumption of a family house is around 10,000 kilowatts per hour. The power output of an intermittent hybrid plant of 10 wells may feed over 700 homes, and by hybrid I mean the combination of three different energy sources: thermal, solar, and natural gas, where natural gas production of energy would be at a specific percentage coming from the total energy of thermal and solar. In a bigger scale, 12,000 wells would provide energy to a big city such as Houston. In the next slides, we will see the economical analysis which will be covered by Dr. Sharma.
Thank you, Jose. In this slide, we are trying to showcase the economic implications of geothermal energy. Here we are comparing a 20-year NPV of thermal solar intermittent circulation with pentane. Intermittent circulation is you have 12 hours of geothermal injection and then 12 hours of solar power production. The scenario is 20 duck well versus 20 new wells. Duck wells are drilled but uncompleted wells, and the workover cost are considered to be $500,000. And for new wells, we assume $3 million per well cost. So in this scenario, you have NPV for $1.2 million with a carbon tax of $150 for a duck well, and for a new well, you have negative $1.3 million with the carbon tax of $150. So in this comparison, we are just trying to showcase that if you are utilizing duct wells where the workover costs are significantly lower than the well cost, you stand to make more money in that scenario. In the new well scenario, because of the higher well cost, you will lose money. Now we wanted to consider a scenario, how do we scale up the geothermal power production? So here we wanted to consider a scenario of 900,000 homes, which is very similar to the situation that you'll have in a city like Houston. And we were applying a hybrid approach where you have a thermal, solar and grid power supply. So grid power supply is the redundancy required for a big application like Houston City. And if you compare a 20-year NPV in that scenario, you'll make $20 billion in 20 years, in 20 years period. And similarly, the LCOE for that project will come out to be 13 to 14 cents per kilowatt hour. If you consider a slightly different scenario, so instead of a big city like Houston, now you're going to look at a mid-size city like Odessa Midland. One additional advantage here is that you will have a lot of duct wells available there. So in that scenario, similar hybrid approach, solar, thermal, and grid power, the 20-year project will yield $2 billion, $2.5 billion almost in NPV, and LCOE is again around 13 to 14 cents per kilowatt hour. So in both scenarios, I can see in a big city like Houston scenario or a mid-sized city like Odessa Midland, you stand to make a lot of money. It's an economical project, and it is also taking care of the redundancy required for a scale-up application. Now, if we talk about something different application, now we are talking about direct application. So here we are not generating electricity from geothermal power, but we are using the heated water into other application. So the geothermal gradient that we consider in this application is slightly lower. So the geothermal gradient is 0.05 degrees C per meter. And in that scenario, we compare two different fluids, water and pentane. And we also compare two different injection strategy. One is the intermittent and one is continuous. So when you look at the continuous injection, in case of water, you see it starts around 80 degree and then it drops drastically to 40 degrees C in 20 years. But in case of water, if you go for a intermittent injection strategy, you'll start around 80, but you can maintain the temperature for a longer time. In case of pentane, it is even better because in first year you're somewhere around 100 degrees C, and you're going to maintain with the intermittent injection strategy the temperatures of around 80 to 85 degrees C. So there is a lot of potential in terms of producing heat water or heated fluid. And where do we use it? So if you look at the table on the right, we have different water temperature required for different kinds of industry. So there is all kinds of industry which will benefit for all the different kind of temperature we discussed in this study. So there is a lot of potential of applying the direct energy. So what about the economic implications of the direct use case? So here we wanted to compare same 20-year NPV scenario for a direct use with intermittent circulation. So 12 hours on, 12 hours off kind of circulation. Geothermal gradient I mentioned is the lower than the power generation scenario. So you have 0.05 degrees C per meter geothermal gradient. So in this scenario, we compared different fluids. So we compared water and pentane. So if you look at NPV for water in a 20-year time frame, you get somewhere around $2 million. But similarly, as we saw in temperature scenario, pentane produces a very high temperature. So the NPV from the pentane scenario will be somewhere around $7 million. So in both scenarios, you see it's more positive, and in pentane, because of the higher temperature, you stand to make it's more economical in that sense. So in summary, we wanted to just reiterate some of the major findings from this study. So first of all, cyclic fluid circulation strategy involving night, thermal and day solar, it appears technically sound. Then thermal solar hybrid approach with natural gas or grid supplying 25% of the power, both appears economically and strategically attractive, especially considering the fact that they are also providing redundancy for our systems. And the value proposition in agriculture food industry with hot water is encouraging, as we saw even in a lower geothermal gradient scenarios. It will still economically attractive. So these are some key findings from the study. Now, thank you so much for your time, and we would love to take some questions now. Thank you.